Welcome to Dark Cosmos Theory. Today we're diving into something that will fundamentally challenge your sense of scale in the universe. We're talking about a cosmic leviathan so massive that calling it big feels like calling the ocean damp. This galaxy isn't just large, it's incomprehensibly vast in ways that will force your brain to confront the limits of human imagination. Before we begin this journey into the incomprehensible, I'd appreciate it if you could hit that like button and subscribe to the channel. Your support helps us continue exploring these mind-bending corners of the universe together. And drop a comment letting us know where you're watching from around the world. It's always fascinating to see how far our cosmic community reaches. Let's start with something familiar. You know Earth. You've walked on it, lived your entire life on its surface. Earth seems pretty substantial when you're standing on it. Now imagine Jupiter, which could swallow over 1,300 Earths. Our Sun makes Jupiter look tiny, capable of containing roughly 1,000,000 Earths inside its fiery bulk. Already we're dealing with numbers that don't quite feel real anymore. But keep going. Our Milky Way galaxy stretches approximately 100,000 light-years from edge to edge. That distance is so extreme that even travelling at light speed, the universe's ultimate speed limit, you'd need 100,000 years to cross it. That time span exceeds the entire existence of human civilization many times over. Our galaxy hosts somewhere between 200 and 400 billion stars, each potentially surrounded by planets, asteroids, and countless other celestial bodies. The Milky Way represents our cosmic neighbourhood. We orbit around its centre at roughly 500,000 miles per hour, yet completing one full rotation takes approximately 250 million years. During the age of dinosaurs, our solar system hadn't even completed a single galactic orbit. When our Sun last occupied this position in the galaxy, Earth's most advanced life forms were primitive oceanic organisms. That gives you some perspective on just how vast even our home galaxy truly is. Now, what if I told you that everything I just described, this colossal structure we call the Milky Way, is essentially microscopic compared to certain monsters lurking in the depths of space? What if there exists a galaxy so phenomenally enormous that our entire Milky Way would be like a single grain of sand on an endless beach? That galaxy exists. Astronomers call it IC 1101, and it represents something close to the ultimate expression of cosmic scale. This elliptical giant measures somewhere between 4 and 6 million light-years across. Let that penetrate for a moment. If you could somehow replace the Milky Way with IC 1101, this behemoth wouldn't just engulf our galaxy, it would swallow the Andromeda Galaxy sitting 2.5 million light-years away. The Triangulum Galaxy would disappear inside it. All the dwarf galaxies orbiting in our local neighbourhood would become mere specks within this Titan's vast embrace. IC 1101 contains an estimated 100 trillion stars. Our Milky Way tops out at maybe 400 billion stars, meaning IC 1101 possesses roughly 250 times more stars than our entire home galaxy. If you started counting those stars at 1 per second without ever stopping for sleep, food, or rest, you'd need over 3 million years just to count them all. By the time you finished, human civilization as we know it would have risen and fallen multiple times. The story of how we discovered this cosmic colossus begins in 1790 with British astronomer William Herschel. While systematically cataloguing celestial objects, Herschel pointed his telescope toward a region in the constellation Virgo and noticed a faint fuzzy patch of light. He carefully recorded its position and moved on, having no way to understand what he was actually observing. The technology simply didn't exist to measure distances to such remote objects, and the scientific framework hadn't yet developed to recognize it as a separate galaxy entirely. For over a century, that mysterious smudge remained just another nebula in astronomical catalogues. It eventually received the designation IC 1101 when included in an expanded index of celestial objects. Astronomers studied it when possible, but without proper tools to grasp its true nature, it remained one curiosity among thousands. Everything changed during the 20th century as telescope technology advanced dramatically. Astronomers developed techniques for measuring cosmic distances and realized IC 1101 wasn't a nearby gas cloud, but an entirely separate galaxy at a mind-boggling distance. The light we observe from IC 1101 today departed that galaxy over 1 billion years ago. Think about that. When those photons began their journey toward Earth, life here consisted mostly of single-celled organisms. Complex animals hadn't evolved yet. Dinosaurs wouldn't appear for hundreds of millions of years. Every major event in human history happened while that ancient light was still crossing the void between galaxies. As astronomers continued investigating IC 1101, they began understanding why it grew to such staggering proportions. This galaxy didn't achieve its enormous size through normal processes alone. It became a giant through cosmic violence that has persisted for billions of years. IC 1101 is what scientists call a cannibal galaxy. It has been devouring other galaxies. Galactic cannibalism is a process you need to understand through the lens of gravity at cosmic scales. Galaxies don't exist in isolation. They cluster together, held by mutual gravitational attraction. Within these clusters, galaxies move around each other, sometimes passing close, sometimes colliding directly. When two galaxies approach each other, their gravity distorts their shapes. Stars get pulled from normal orbits. Gas and dust compress and stretch. If the galaxies are similar in size, they might merge over hundreds of millions of years, eventually forming a single larger galaxy. But when one galaxy significantly outweighs the other, something different occurs. The larger galaxy simply absorbs the smaller one, stripping away its stars and gas, incorporating all that material into its massive structure. This has been happening to IC 1101 for billions of years. As the largest and most massive galaxy in its cluster, IC 1101 sits at the gravitational center of everything nearby. Smaller galaxies venturing too close get trapped by its enormous gravity. They spiral inward, getting torn apart and consumed over millions of years. Each meal makes IC 1101 slightly bigger, slightly more massive, slightly more dominant. Scientists estimate IC 1101 has experienced at least 76 major mergers throughout its history. 76 times another substantial galaxy fell into this cosmic giant and was absorbed. And those are just the major mergers. Countless smaller dwarf galaxies have also been consumed. Galaxies so diminutive they barely registered as meals for this enormous predator. The evidence for this cannibalistic history is written directly into IC 1101's structure. When you observe a galaxy like our Milky Way, you see beautiful spiral patterns. Those spiral arms are regions where stars actively form, where clouds of gas collapse under gravity to create new stellar nurseries. Spiral galaxies contain lots of gas and dust, the raw materials needed for star formation, and they possess a distinct rotating disk shape. IC 1101 looks nothing like this. It's what astronomers call an elliptical galaxy, meaning it has a smooth oval-shaped appearance with no spiral arms whatsoever. Elliptical galaxies form when spiral galaxies merge together. The violent gravitational interactions during a merger destroy the delicate spiral structure, mixing all the stars together into a more random spherical or oval distribution. The fact that IC 1101 is elliptical tells us it has experienced so many mergers that any original spiral structure it might have possessed has been completely erased. All those collisions, all that gravitational chaos has stirred up the stars like ingredients in a cosmic mixing bowl. What remains is this smooth, featureless giant, a testament to billions of years of galactic consumption. But here's something even more remarkable about IC 1101. Despite containing 100 trillion stars, it's actually a dying galaxy. The stars within it are almost all old. Most of them are what astronomers call red giants or yellow stars, ancient stellar objects that have already burned through most of their fuel. Very few new stars are being born inside IC 1101. This might seem strange at first. With so many stars and so much mass, you might expect IC 1101 to be a hotbed of stellar activity. But remember how it grew so large. Every time it consumed another galaxy, it also consumed that galaxy's gas supply. Gas is the fuel for star formation. Without gas, new stars cannot be born. Over billions of years of cannibalism, IC 1101 has used up or expelled most of its available gas. The mergers themselves were often violent enough to heat the gas to extreme temperatures, making it expand and escape the galaxy entirely, or to compress it so quickly that it all formed into stars at once in brief, intense bursts of activity. Either way, the end result is a galaxy that has run out of raw material. What remains is a quiet giant slowly fading into the cosmic night. The stars that exist now will continue shining for billions of years to come, but as they eventually burn out and die, there will be no new generations to replace them. IC 1101 is like an ancient empire that has conquered all its neighbours but has no children to carry on its legacy. It's massive, powerful, and utterly magnificent. But it's also approaching the end of its active life. At the very heart of IC 1101 lies something even more incredible than the galaxy itself. Sitting at the centre of this cosmic giant is one of the largest known supermassive black holes in the entire universe. Every large galaxy has a supermassive black hole at its core. Our own Milky Way has one called Sagittarius A, which contains about 4 million times the mass of our Sun. The black hole at Andromeda's centre is even bigger, containing somewhere around 100 to 200 million solar masses. But the black hole at IC 1101's centre exists in a completely different category. Scientists estimate it contains somewhere between 40 billion and 100 billion times the mass of our Sun. To put that in perspective, this single black hole might have 25,000 times more mass than the black hole at the centre of our entire Milky Way galaxy. Let me help you understand just how massive this is. If you could somehow weigh Earth, you'd find it has a mass of about 6 trillion kilograms. That sounds substantial until you compare it to the Sun, which is roughly 330,000 times more massive than Earth. Our Sun is a fairly ordinary star by stellar standards. Now multiply the Sun's mass by 50 billion. That's approximately how much mass is packed into the supermassive black hole at IC 1101's centre. All of that mass is compressed into a region of space from which nothing can escape. The gravitational pull at the event horizon, the boundary of the black hole, is so intense that even light itself cannot break free. The size of a black hole's event horizon depends on its mass. For a black hole of 50 billion solar masses, the event horizon would have a radius of roughly 150 billion kilometers. That might sound enormous, and it is. But remember that this is a region containing 50 billion times the mass of the Sun, compressed into what is essentially a point at the centre. To put this in perspective, our entire solar system from the Sun to Neptune's orbit is about 9 billion kilometers across. The event horizon of IC 1101's black hole is roughly 16 times larger than our entire solar system. If you place this black hole where our Sun is, its event horizon would extend well beyond Pluto's orbit, engulfing everything we consider our cosmic home. What would it be like near this monstrous black hole? The physics of such extreme environments is bizarre and counterintuitive. Time itself would pass differently near the event horizon compared to far away. Someone falling toward the black hole would see the outside universe speed up, while an outside observer would see the falling person slow down and appear to freeze as they approach the horizon. Inside the event horizon, all directions lead toward the singularity at the center. Space and time themselves become so warped that the concept of escaping becomes meaningless. The singularity, a point of theoretically infinite density, would tear apart anything that fell in, stretching it into long thin strands through a process physicists have nicknamed spaghettification. But here's something remarkable. Despite its enormous size and terrifying properties, the black hole at IC 1101's center is currently relatively quiet. It's not actively devouring huge amounts of matter. There's no brilliant accretion disk swirling around it, no powerful jets shooting into space at nearly light speed. The black hole is there, waiting, but it has already consumed most of the material that was easily within reach. This quietness is actually related to the same phenomenon that has stopped IC 1101 from forming new stars. Most of the gas in the galaxy has already been used up. And without gas falling toward the center, the black hole has little to eat. Occasionally, a star wanders too close and gets torn apart, providing a brief meal. But these events are rare. The black hole, like the galaxy that hosts it, is a giant in repose, powerful but dormant. There are still traces of the black hole's past activity. Astronomers have detected radio emissions at IC 1101's center. This radio emission comes from relativistic jets, streams of particles, accelerated to nearly light speed and ejected from the vicinity of the black hole. These jets are powered by the black hole's rotation and magnetic fields, and they can carve out enormous cavities in the surrounding gas. Images from X-ray telescopes show these cavities clearly. They're bubbles of very hot, very thin gas blown outward by the energy released near the black hole. Some of these bubbles are millions of light years across, testimony to periods in the past when the black hole was much more active than it is today. The energy required to inflate these bubbles is staggering, equivalent to the total energy output of billions of stars over millions of years. This kind of feedback between supermassive black holes and their host galaxies is one of the most active areas of research in modern astrophysics. Scientists now believe that supermassive black holes play a crucial role in regulating galaxy growth and evolution. When gas flows toward a galaxy's center, the black hole can release enough energy to heat that gas and push it outward, preventing it from forming stars. In IC 1101's case, this feedback may be partly responsible for the galaxy's current state. The black hole has helped shut down star formation by heating gas and preventing it from cooling and collapsing. The giant galaxy and its giant black hole have reached a kind of equilibrium, each one having shaped the other over billions of years of shared evolution. Black holes grow by consuming matter that falls into them. When galaxies merge, the supermassive black holes at their centers eventually find each other and merge as well. Over the course of IC 1101's long history of galactic cannibalism, its central black hole has been fed again and again. Every galaxy that IC 1101 consumed added to the mass of this growing monster. The process by which two supermassive black holes merge is fascinating and violent. When two galaxies collide, their central black holes don't immediately find each other. They're separated by vast distances and surrounded by billions of stars. But as the merger progresses, gravitational friction with the surrounding stars causes the black holes to spiral toward the center of the combined galaxy. Eventually, the two black holes get close enough to form a binary system, orbiting around each other. As they orbit, they lose energy through gravitational waves, ripples in the fabric of space-time itself. These gravitational waves carry energy away from the binary, causing the orbit to shrink. the black holes spiral closer and closer, orbiting faster and faster, until finally they merge in a catastrophic event that releases enormous amounts of energy. When two supermassive black holes merge, the gravitational waves they produce are among the most powerful events in the universe. The final merger releases more energy than all the stars in a typical galaxy combined, though most of this energy is in the form of gravitational waves rather than light. These waves ripple outward at the speed of light, stretching and squeezing space itself as they pass. We've only recently developed the technology to detect gravitational waves. The first direct detection came in 2015, when the LIGO observatories measured waves from two stellar mass black holes merging about 1 billion light-years away. Since then, dozens of gravitational wave events have been observed, opening up an entirely new way of studying the universe. IC 1101's black hole has experienced dozens of such mergers over its long history. Each merger added mass and altered the black hole's spin. The process of multiple mergers also affected the surrounding galaxy, as the merging black holes flung stars outward through gravitational interactions. This is probably why IC 1101's core is so large, yet relatively faint compared to galaxies of similar size. Now, I want to take you on a journey to help you truly appreciate the scale of what we're discussing. Imagine you could somehow travel from one end of IC 1101 to the other. You would need to cross somewhere between 4 and 6 million light-years. Remember, light travels at about 6 trillion miles per year. Even at that incomprehensible speed, crossing IC 1101 would take millions of years. But let's try another comparison. The Voyager 1 spacecraft, launched by NASA in 1977, is the fastest human-made object ever to leave our solar system. It's travelling at about 38,000 miles per hour relative to the Sun. At that speed, Voyager 1 would take about 80,000 years just to reach Proxima Centauri, the nearest star to our Sun, which is only about 4 light-years away. To cross the entire Milky Way at Voyager 1's speed would take about 2 billion years. And to cross IC 1101, you would need somewhere between 80 billion and 120 billion years. That's more time than the universe has even existed. Even with our fastest spacecraft, crossing this single galaxy would be completely impossible within any conceivable time frame. Here's another way to think about it. If you could shrink the Milky Way down to the size of a dinner plate, about 10 inches across, then IC 1101 would be the size of a large swimming pool. Our entire galaxy, with all of its hundreds of billions of stars, with the spiral arms where we make our home, would be just a tiny dish floating in a vast sea. Or consider this. Light from IC 1101 has travelled for over 1 billion years to reach us. In all that time, light has been continuously streaming away from this galaxy in every direction. Every second, IC 1101 radiates enough light to travel about 186,000 miles. Over 1 billion years, that light has travelled 1 billion light-years, which is about 6 billion trillion miles. And it's only now just arriving at our telescopes, ancient photons that left their home galaxy when Earth was still in its earlier stages of complex life. The discovery and study of IC 1101 wouldn't have been possible without tremendous advances in telescope technology. In the early days of astronomy, telescopes were limited by the size of their lenses and mirrors. Larger telescopes could gather more light and see fainter objects, but there were practical limits to how big you could make a telescope on the ground. Everything changed with the launch of the Hubble Space Telescope in 1990. Floating above the atmosphere, Hubble could capture images with incredible clarity. Over the decades since its launch, Hubble has observed IC 1101 multiple times, revealing details about its core, its surrounding halo of stars, and its relationship to other galaxies in its cluster. More recently, astronomers have used a variety of other telescopes to study IC 1101, at different wavelengths of light. Radio telescopes have detected the emission from its central black hole. X-ray telescopes have observed the hot gas that fills the cluster around it. Infrared telescopes have peered through dust to study the stellar populations within the galaxy. Each new observation adds to our understanding of this cosmic giant. But there's still much we don't know. The exact number of stars in IC 1101 remains uncertain because counting stars in such a distant galaxy is incredibly difficult. The precise size of the galaxy depends on how you define where it ends, since galaxies don't have sharp boundaries but gradually fade into the darkness of intergalactic space. What we do know is that IC 1101 represents something close to an upper limit for how large galaxies can get. There may be slightly larger galaxies out there waiting to be discovered. In fact, in 2022, astronomers announced the discovery of a galaxy called Alcyonius, which has radio lobes extending across an astonishing 16 million light-years. But Alcyonius is a special case. Its enormous size comes from giant jets of material shooting out from its central black hole, not from stars and normal galactic material. When it comes to the actual body of a galaxy, the collection of stars and gas and dark matter that make up its substance, IC 1101 remains one of the largest ever found. The story of IC 1101 also tells us something profound about the nature of the universe and the passage of cosmic time. Galaxies don't form all at once. They grow over billions of years through a process of accumulation and merger. Small galaxies form first from collapsing clouds of primordial gas. Those small galaxies then merge together to form larger ones. Larger galaxies merge to form even larger ones, and on it goes, with the biggest galaxies growing ever larger by consuming their smaller neighbours. This process is called hierarchical structure formation, and it's one of the fundamental principles of modern cosmology. The universe builds things from the bottom up, starting small and growing large through countless mergers over cosmic time. IC 1101 is simply the most extreme example of this process that we've found so far. It has had billions of years and a perfect location at the centre of a rich galaxy cluster to grow to its incredible size. But the growth cannot continue forever. IC 1101 has already consumed most of the galaxies that were close enough to fall into it. Those that remain are either too far away or moving too fast to be captured. The surrounding cluster is slowly spreading out due to the expansion of the universe, carrying potential victims farther and farther from IC 1101's gravitational reach. At the same time, the larger universe is changing in ways that will eventually affect every galaxy, including this enormous one. Space itself is expanding, and not just expanding but accelerating in its expansion. This acceleration is driven by something scientists call dark energy, a mysterious force that makes up about 68% of the total energy in the universe, but whose nature we don't understand at all. For most of the 20th century, astronomers assumed that the expansion of the universe was slowing down. This made intuitive sense. Everything in the universe is pulling on everything else through gravity. You would expect all that gravitational attraction to act like a brake, gradually slowing the expansion that began with the Big Bang. In 1998, two independent teams of astronomers made a shocking discovery. They were measuring the expansion rate of the universe by observing distant supernovae, using them as standard candles to calculate cosmic distances. What they found was completely unexpected. The universe wasn't slowing down, it was speeding up. Scientists named this mysterious force dark energy, though the name tells us very little about what it actually is. We know that dark energy makes up about 68% of all the energy in the universe. We know that it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. We know that its effects become more important over time as the universe expands and ordinary matter becomes more spread out. For IC 1101, this means that its days of growth through galactic cannibalism are numbered. Eventually, there will simply be no more galaxies left for it to consume. It will become isolated, a lonely giant floating in an ever-emptying universe, watching as one by one the other galaxies fade from view. IC 1101 sits in the Abell 2029 galaxy cluster, surrounded by hundreds of other galaxies. These galaxies are bound together by gravity, orbiting around their common center of mass. For now, gravity is strong enough to hold the cluster together against the expansion of space. But in about 100 billion years, the expansion will have accelerated to the point where galaxies outside the local supercluster will start to disappear over the cosmic horizon. From IC 1101's perspective, the sky will start to empty. One by one, distant galaxy clusters will fade from view, their light no longer able to reach across the expanding void. Within the Abell 2029 cluster, things will be different for a while longer. The galaxies there are close enough and bound tightly enough that they'll stay together even as the larger universe empties out. Over the next several billion years, these galaxies will continue to interact, merge, and evolve. IC 1101 might still consume a few more victims, growing slightly larger even as the rest of the universe slips away. But eventually, even the galaxies within the cluster will merge together. The same processes that built IC 1101 will continue, drawing the remaining galaxies toward the center where they'll be absorbed into an even larger combined structure. In the very long run, perhaps in several hundred billion years, all the galaxies in the Abell 2029 cluster might merge into a single enormous galaxy, even larger than IC 1101 is today. By that time, however, the universe beyond the cluster will be essentially empty. No light from distant objects will be reaching the cluster anymore. The night sky, if any observers still existed, would show only the stars of the local merged galaxy against a backdrop of absolute blackness. This is the isolation that awaits IC 1101 and every other structure in the universe, cut off from everything else by the relentless expansion of space. Each island of matter will be alone with itself as the eons roll by. But even this is not the final fate of IC 1101. Over the next 100 trillion years, the stars in IC 1101 will slowly burn out. The massive blue stars went long ago, exploding as supernovae or collapsing into black holes. The middle-sized stars like our Sun will puff up into red giants, shed their outer layers as beautiful nebulas, and then fade away as white dwarfs. Even the smallest, longest-lived stars, the red dwarfs that burn their fuel so slowly they can shine for trillions of years, will eventually exhaust their hydrogen and go dark. The most numerous stars in any galaxy are red dwarfs. These tiny stars burn their fuel so slowly that they can shine for trillions of years. In IC 1101, with its 100 trillion stars, there are untold numbers of red dwarfs. These tiny dim stars will be the last to go out. For trillions of years after the larger stars have died, the red dwarfs will continue to burn, providing the only light in an otherwise darkening galaxy. But even red dwarfs have limits. The smallest red dwarfs, with perhaps 8% of the Sun's mass, can burn for up to 10 trillion years. That's about 700 times the current age of the universe. But eventually even they will exhaust their hydrogen fuel and fade into darkness. Scientists estimate that star formation in the universe will effectively cease in about 100 trillion years. By that time, the gas and dust needed to make new stars will have been used up or dispersed too thinly to collapse. No new stars will be born to replace the ones that have died. The era of starlight will be over. One by one, the 100 trillion stars of IC 1101 will wink out. The galaxy will grow dimmer and dimmer over timescales that make the current age of the universe seem like the blink of an eye. Where once there was a blaze of stellar light, there will eventually be nothing but the cold, dark remnants of dead stars, white dwarfs, neutron stars, and black holes drifting through an ever-expanding void. The universe at this stage will be a dark place, but not an empty one. All those stellar remnants will still exist. They'll orbit through the merged remnant of what was once IC 1101 and its cluster companions. The galaxy will be a ghost of its former self, populated by the corpses of stars rather than by living, burning suns. But even this is not the end. Over even longer timescales, measured in years with so many zeros that writing them out would fill pages, even these stellar corpses will decay. White dwarfs will slowly cool until they become black dwarfs, objects that no longer emit any light at all. And the black holes, including that enormous monster at the center of IC 1101, will slowly evaporate through a process called Hawking radiation. Stephen Hawking discovered that black holes aren't truly black. They slowly leak particles and radiation over immense time spans, gradually shrinking as they do so. The rate of Hawking radiation is incredibly slow for large black holes. A black hole with the mass of our Sun would take about 10 to the 67th power years to evaporate. But the supermassive black hole at the center of IC 1101 is billions of times more massive than the Sun, and the time for it to evaporate is correspondingly longer. A black hole containing 50 billion solar masses would take something like 10 to the 100th power years to evaporate, or maybe even longer. That's a Google years, a 1 followed by 100 zeros. To write out that number in full would require more paper than exists on Earth, but even this time is not infinite. Eventually, trillions upon trillions upon trillions of years from now, even the supermassive black hole at the heart of IC 1101 will have radiated away its last bit of energy and disappeared from the universe in a final burst of Hawking radiation. When that finally happens, there will be nothing left of IC 1101 at all. No stars, no black holes, no remnants of any kind, just the particles and radiation that once made up a galaxy spreading out through an ever-expanding, ever-cooling, ever-darkening universe. This vision of the future might seem bleak, but I find something strangely beautiful about it. IC 1101 exists right now, in this brief moment of cosmic history when stars still shine and galaxies still glow. It has existed for billions of years and will continue to exist for billions more. In the grand sweep of cosmic time, the era of stars and galaxies is just a passing phase, a brief flowering of complexity between the chaos of the early universe and the cold emptiness of the far future. We're lucky enough to exist during this flowering. We're lucky enough to have evolved intelligence, built telescopes, and pointed them at the sky. We're lucky enough to have discovered IC 1101 and to understand, at least in part, what it is and how it came to be. In all the vast history of the universe, stretching from the Big Bang to the final heat death, this moment right now is special. It's the moment when the universe has developed the ability to look at itself and wonder. And what we see when we look at IC 1101 is the grandest scale on which the universe has assembled matter into organized structures. We see billions of years of cosmic history written in stars. We see the results of countless galactic mergers, countless collisions, countless acts of gravitational violence that have somehow produced something magnificent. Let me bring us back closer to home for a moment. Our own Milky Way isn't immune to the forces that shaped IC 1101. We too are participating in the cosmic dance of galactic interaction and merger. Right now, as you're reading these words, our galaxy is in the process of consuming several smaller galaxies. The Canis Major dwarf galaxy is being ripped apart and absorbed into the Milky Way. The Sagittarius dwarf galaxy is being stretched and distorted by our gravitational pull. Streams of stars from past victims can be traced across our sky, ghostly reminders of galaxies that once existed as separate entities, and in the future, an even more dramatic event awaits. The Andromeda Galaxy, our nearest large neighbour, is heading toward us. Scientists have long believed that in about 4 to 5 billion years, the Milky Way and Andromeda will collide and eventually merge into a single larger galaxy. If the merger does happen, the results would be spectacular, at least on cosmic timescales. The collision itself wouldn't be violent in the way you might imagine. Stars are so far apart that the chances of any two stars actually hitting each other are essentially zero. But the gravitational effects would be dramatic. The spiral structures of both galaxies would be destroyed. Gas clouds would be compressed, triggering enormous bursts of star formation. The two supermassive black holes at the centers of each galaxy would eventually find each other and merge, releasing gravitational waves that would ripple across the universe. Over billions of years, the chaos would settle down. What was once the Milky Way and what was once Andromeda would blend together into a single large elliptical galaxy, much like IC 1101, but much smaller. Future astronomers, if any exist, might look back at old records and marvel that their smooth, featureless home galaxy was once two beautiful spirals dancing through the void. I want to return now to the question of what IC 1101 tells us about our place in the universe. When you look up at the night sky, you might feel small. You might feel insignificant in the face of such vastness. But I think the existence of IC 1101 actually tells us something hopeful about our situation. First, consider that we can know about IC 1101 at all. A galaxy more than 1 billion light-years away, containing 100 trillion stars, and we've figured out how big it is, how it formed, what lies at its centre. That's remarkable. Human beings, living on a small rocky planet orbiting an ordinary star in an unremarkable part of an average spiral galaxy, have somehow developed the ability to understand objects so far away that their light left before complex life existed on Earth. This ability to understand is not nothing. In a universe of mindless matter and energy, of particles bouncing around according to physical laws, somehow here on Earth consciousness has emerged. Minds that can wonder, question, investigate, and learn. Whatever else we are, we're the part of the universe that has woken up and started asking questions about itself. Second, consider that IC 1101, for all its enormity, is made of the same stuff we are. The stars in IC 1101 are fusion reactors just like our Sun. They burn hydrogen into helium and heavier elements just like stars do everywhere. The atoms in those distant stars are the same kinds of atoms that make up our bodies. There's a continuity here, a connection between us and everything else in the cosmos. We're not separate from the universe. We're part of it. The same processes that built IC 1101 built us. The same atoms that shine in distant galaxies shine in our eyes. We're not observers of the universe from outside. We're the universe observing itself from within. IC 1101 is a testament to what's possible in our universe. It's proof that matter and energy, following simple physical rules over billions of years, can organize itself into structures of staggering complexity and beauty. If the universe can produce IC 1101, what else might it be capable of? What other wonders exist out there that we haven't yet discovered? Every discovery we make, every galaxy we study, every black hole we observe expands our sense of what's possible. A few centuries ago, people thought Earth was the center of everything. Then we learned that we orbit the Sun. Then we learned that the Sun is one star among hundreds of billions in our galaxy. Then we learned that our galaxy is one of trillions. Each step has made us smaller in some sense, but it has also made the universe grander, more interesting, more worthy of awe. IC 1101 is another step in that journey. It shows us that the universe can build things far larger than we ever imagined. As we wrap up this exploration of the biggest galaxy ever discovered, I want to leave you with one final image. Imagine yourself floating in space, somewhere near the edge of IC 1101. Around you in every direction, stars stretch out toward infinity. Not hundreds, not thousands, not millions, but trillions of stars. Each one is a sun. Each one might have planets. Each one has been shining for billions of years. You cannot see the center of the galaxy from here. It's too far away, hidden behind countless curtains of stars. You cannot see the edge either. The galaxy fades gradually into the darkness of intergalactic space with no clear boundary. You're lost in a sea of light, adrift in a structure so vast that crossing it would take millions of times longer than human civilization has existed. And yet, from a small rocky planet more than 1 billion light-years away, beings who live for less than a cosmic instant have figured out that this place exists. They've measured its size, counted its stars, found the black hole at its heart. They've traced its history back billions of years and projected its future trillions of years hence. That's perhaps the most amazing thing of all. Not that IC 1101 exists, but that we know it does. The biggest galaxy we've ever discovered is bigger than your imagination. But the fact that you can imagine it at all, that you can hold in your mind a picture of 100 trillion stars spread across millions of light years, that you can wonder about its past and future, that is perhaps the most amazing thing of all. Let me dive deeper into the cosmic neighborhood that IC 1101 inhabits, because understanding where this giant lives helps us understand how it became so massive in the first place. IC 1101 doesn't float alone in the void. It resides at the heart of the Able 2029 galaxy cluster, one of the richest and most massive galaxy clusters in the observable universe. Galaxy clusters represent some of the largest gravitationally bound structures in existence. They can contain hundreds to thousands of individual galaxies, all held together by their combined gravitational pull. The space between these galaxies isn't empty either. It's filled with incredibly hot gas, heated to temperatures of tens of millions of degrees by the gravitational energy released as the cluster formed. This hot gas, called the intracluster medium, is so hot that it emits X-rays. When astronomers point X-ray telescopes at galaxy clusters, they see this glowing gas surrounding the galaxies like a cosmic fog. In the Able 2029 cluster, this gas is particularly concentrated around IC 1101 at the cluster's center, forming a kind of atmosphere around the giant galaxy. The presence of this hot gas has profound implications for IC 1101's evolution. Hot gas can cool down over time, radiating away its energy as X-rays. When it cools enough, it can fall into the central galaxy and potentially fuel new star formation. In some galaxy clusters, astronomers have observed enormous flows of cooling gas, hundreds of solar masses worth per year streaming into the central galaxy. But in IC 1101's case, something is preventing this cooling flow from triggering a new burst of star formation. The leading theory is that the supermassive black hole at IC 1101's center is responsible. When gas falls toward the black hole, some of it gets heated up and blown back out into the cluster. This creates a feedback loop where the black hole regulates the gas supply, preventing too much from accumulating and forming stars. We can actually see evidence of this feedback in observations of IC 1101 and its surroundings. There are cavities in the hot gas around the galaxy, bubbles that have been blown by jets from the central black hole. These cavities are millions of light-years across, enormous voids carved out of the intracluster medium by the energy output of the black hole. This feedback mechanism is thought to be important for understanding why massive elliptical galaxies like IC 1101 aren't forming stars today. Without the black hole regulating the gas supply, cooling flows would deliver enough material to trigger substantial star formation. But the black hole acts like a thermostat, heating up gas whenever too much starts to cool, keeping the galaxy in a kind of permanent energy balance. The location of IC 1101 at the centre of such a rich cluster also explains how it grew so large. Being at the cluster's gravitational centre meant that IC 1101 was perfectly positioned to intercept and consume other galaxies as they spiralled inward. Over billions of years, the cluster has acted like a funnel, channeling smaller galaxies toward IC 1101, where they were absorbed and incorporated into its growing mass. This process of cluster formation and central galaxy growth is happening throughout the universe. Wherever we find rich galaxy clusters, we typically find a massive elliptical galaxy at the center, bloated from billions of years of consuming its neighbors. IC 1101 is simply the most extreme example we've discovered so far. Now let's talk about how astronomers actually measure something as distant and massive as IC 1101. Distance measurement in astronomy is one of the most challenging and fundamental problems in the field. How do you determine how far away something is when you can't travel there and you can't stretch out a measuring tape? For relatively nearby objects, astronomers use a technique called parallax. As Earth orbits the Sun, our perspective on nearby stars changes slightly. By measuring how much a star appears to shift against the background of more distant stars over the course of a year, astronomers can calculate how far away it is. This works well for stars within a few thousand light years, but for anything more distant, the parallax shift becomes too tiny to measure accurately. For more distant objects, astronomers use what's called a cosmic distance ladder, a series of techniques that build on each other. One crucial rung involves a special type of star called a Cepheid variable. These stars pulsate in brightness with a regular period, and the period of their pulsation is directly related to their intrinsic luminosity. By measuring how bright a Cepheid appears and how fast it pulsates, astronomers can calculate how far away it is. But IC 1101 is too distant even for Cepheid variables. At over 1 billion light-years away, individual stars are far too faint to detect. For such extreme distances, astronomers rely on even brighter standard candles, particularly a type of exploding star called a Type Ia supernova. These explosions occur when a white dwarf star accumulates too much matter from a companion and detonates in a thermonuclear explosion. Because the conditions for this detonation are similar from one supernova to another, they all reach roughly the same peak brightness. By measuring how bright a Type Ia supernova appears, astronomers can estimate how far away its host galaxy is. Another crucial technique involves measuring the redshift of a galaxy's light. As the universe expands, light from distant objects gets stretched to longer wavelengths. This shifts the light toward the red end of the spectrum, hence the name redshift. The more distant an object is, the more the universe has expanded since its light was emitted, and the greater its redshift. By measuring the redshift of light from IC 1101, astronomers have determined that it's about 1.04 billion light-years away. This measurement, combined with observations of the galaxy's apparent size and brightness, allows them to calculate its physical properties like diameter and stellar mass. Each of these techniques has uncertainties, and measuring cosmic distances is not a simple matter. Astronomers continue to refine their methods, using new observations and improved understanding of the underlying physics. The distance to IC 1101 might be revised as better data becomes available, but the basic picture of an enormous galaxy sitting over 1 billion light-years from Earth is well established. There's something profoundly strange about observing an object that's 1 billion light-years away. When we look at IC 1101, we're not seeing the galaxy as it is today. We're seeing it as it was over 1 billion years ago, when the light we detect today, first began its journey toward Earth. 1 billion years ago, Earth was a very different place. Complex animal life hadn't yet evolved. The planet was populated by single-celled organisms and perhaps simple multicellular life, but nothing that would be recognizable as an animal or plant. The continents were in different positions. The atmosphere had a different composition. It was an alien world by any measure. During all the time since then, light from IC 1101 has been travelling through space. It crossed the vast emptiness between galaxies, occasionally passing through clouds of intergalactic gas or being bent slightly by the gravity of intervening objects. It travelled at the fastest speed anything can travel, yet the distance was so immense that it took over 1 billion years to arrive. The IC 1101 we see in our telescopes might be very different from IC 1101 as it exists right now. Over 1 billion years, much could have changed. Stars that were shining then might have burned out by now. New stars might have formed, though probably not many given IC 1101's depleted gas supply. The central black hole might have experienced new feeding events or gone through periods of dormancy. We have no way of knowing what IC 1101 looks like at this very moment. The information about its current state won't reach us for another 1 billion years. In a very real sense, we're archaeologists of the cosmos, studying the past rather than the present. This time delay is both a limitation and an opportunity. It limits our ability to understand the current state of the universe, but it allows us to study cosmic history directly. By looking at galaxies at different distances, and therefore at different points in the past, astronomers can piece together how galaxies have changed over cosmic time. IC 1101, seen as it was 1 billion years ago, provides a snapshot of a giant galaxy in a particular stage of its evolution. Other giant elliptical galaxies, some closer and some farther, provide additional snapshots. By combining all of these observations, astronomers build up a picture of how such galaxies form and change over time. Let me share some thought experiments to help make the scale of IC 1101 feel more tangible. Imagine you wanted to visit every star in IC 1101. You have an incredibly fast spaceship that can travel at the speed of light, the universe's ultimate speed limit. Even at that impossible speed, if you spent just 1 second at each star before moving to the next, it would take you over 3 million years to visit all 100 trillion stars. Or consider this. Suppose you wanted to count every star in IC 1101 out loud, one number per second, without ever stopping for sleep or rest. You start counting 1, 2, 3, and so on. When would you finish? After more than 3 million years of continuous counting. If you had started counting when the first humans evolved, you'd still have millions of years of counting ahead of you. Here's another way to think about the size. The average human walking speed is about 3 miles per hour. At that pace, walking 24 hours a day without stopping, it would take you about 50 trillion years to walk from one side of IC 1101 to the other. That's over 3,000 times longer than the current age of the universe. You could walk for the entire history of everything that has ever happened, from the Big Bang until now, and you would have covered less than 1/3000th of the distance across this single galaxy. The scale is so vast that even these comparisons don't really capture it. They just give us a sense of how thoroughly these numbers exceed human comprehension. Now let's talk about the question that's probably on many minds. Could there be life in IC 1101? With 100 trillion stars, could this galaxy be home to intelligent civilizations? This is a question that science cannot answer directly right now. We have no way of detecting life in distant galaxies. We barely have the technology to look for life in our own solar system, let alone in galaxies 1 billion light years away. But we can think about what the numbers suggest. If life requires planets, and planets orbit stars, then a galaxy with more stars should have more potential homes for life. The Milky Way might have somewhere between 100 billion and 400 billion planets. If even a tiny fraction of those planets are suitable for life, there could be millions of worlds with living things in our galaxy alone. Scale that up to IC 1101. With 100 trillion stars, this galaxy could have hundreds of trillions of planets. Even if only 1 in a billion of those planets developed life, that would still mean hundreds of thousands of living worlds. Even if only 1 in a trillion developed intelligent life capable of building civilizations, that would mean 100 civilizations in IC 1101. Of course, these numbers are based on assumptions we cannot verify. We don't know how common life is in the universe. We don't know how often life develops intelligence. We don't even know for certain that life requires planets like ours, or that it requires water, or that it's based on carbon chemistry. What we can say is that IC 1101 offers an enormous canvas for whatever processes might lead to life. A galaxy that size has been producing stars for billions of years. Heavy elements, the carbon and oxygen and iron that living things need, have been manufactured in stellar cores and scattered through supernovae countless times. If intelligent life does exist in IC 1101, what might they think when they look up at their night sky? Their view would be dramatically different from ours. Where we see a relatively sparse field of stars with a band of the Milky Way stretching across the heavens, they would see stars everywhere, in every direction. The density of stars in an elliptical galaxy like IC 1101 is much higher than in the disk of a spiral like ours. Near the centre of IC 1101, the night sky would be ablaze with light. Stars would crowd so closely together that there might not be any true darkness at all. The glow of billions upon billions of nearby stars would fill the sky with a perpetual twilight. Further out from the centre, conditions would be more like what we experience, but still different. No spiral arms would trace patterns across the sky. No central band of light would mark the plane of a galactic disk. Instead, the stars would be distributed in a more spherical pattern, surrounding any observer in a shell of stellar light. Would such beings know about the history of their galaxy? Would they have discovered that their home was built from the remains of dozens of smaller galaxies consumed over billions of years? Would they have detected the enormous black hole at their galaxy's centre, or figured out that their cosmos was billions of years old? We cannot know. But it's fascinating to think that somewhere in IC 1101, on one of hundreds of trillions of possible planets, intelligent beings might be asking the same questions about the universe that we ask here on Earth. They might be looking out at the surrounding space, seeing other galaxy clusters in the distance, wondering if those distant smudges of light contain other minds. The universe is vast beyond comprehension, and the possibilities it contains are equally vast. Every galaxy we study reminds us of this vastness and challenges us to think about our place within it. IC 1101 represents not just a single object, but a symbol of everything we've learned about the cosmos, and everything we still have yet to discover. Before we close, I want to reflect on what it means that we can study IC 1101 at all. Think about the chain of events that had to occur for this knowledge to exist. First, the universe had to form in such a way that allowed for the existence of galaxies. Then, one particular galaxy had to grow to extraordinary size through billions of years of mergers. Then, on a small planet orbiting an ordinary star in a completely different galaxy, life had to emerge. That life had to evolve intelligence. That intelligence had to develop curiosity about the stars. That curiosity had to drive the development of ever more powerful telescopes. And finally, someone had to point one of those telescopes at just the right patch of sky. Every step in that chain was improbable. The fact that it happened at all is remarkable. And the fact that we can now sit here and discuss a galaxy 1 billion light years away, knowing how big it is, how old it is, what it's made of, and how it will die, represents one of the greatest achievements of human thought. IC 1101 will never know that we discovered it. Galaxies don't have consciousness or awareness, but we know, and in knowing, we complete a circuit that connects human consciousness to cosmic grandeur. We are tiny, yes. We are brief, yes. But in the brief moment of our existence, we can reach out across 1 billion light years and touch the largest galaxy ever discovered. That reach is our glory. When you next look up at the night sky, remember IC 1101. You cannot see it with your eyes. It's far too distant and too faint for human vision. But it's there, in the direction of the constellation Virgo, shining with the light of 100 trillion stars. It has been there for billions of years, and it will remain there for billions more. Long after our sun has burned out, long after Earth has been consumed by an expanding red giant, IC 1101 will still be there, slowly fading into the cosmic night, but not yet gone. We are part of a universe that contains such wonders. We are made of the same stuff as IC 1101 stars, formed by the same processes, governed by the same laws of physics. In studying that distant giant, we learn about ourselves and our place in the grand story of cosmic evolution. The biggest galaxy we have ever discovered is bigger than your imagination, but the fact that you can imagine it at all, that you can hold in your mind a picture of 100 trillion stars spread across millions of light years, that you can wonder about its past and future, and possible inhabitants, that is perhaps the most amazing thing of all. Thank you for joining me on this journey through the biggest galaxy ever discovered. If this exploration has helped you see the universe in a new way, please consider leaving a comment letting us know what you think about our place in a cosmos that contains such wonders. Until next time, keep looking up and keep wondering about the magnificent universe we call home.